Hello and welcome to the session. Principles of Computer Systems. LO3. Be able to design and implement simple state machines. How do computer systems manage complex tasks reliably? State machines offer a structured way to model and control system behavior. This video explores the principles, design, and implementation of state machines in computer systems. State machines model system behavior through defined states. Each state represents a specific situation the system can be in. Transitions occur based on inputs or events, moving the system from one state to another. Outputs or actions are associated with states or transitions. This structured approach ensures predictable system behavior. More machines have outputs dependent only on the current state. This makes them easier to test and debug. Mealy machines, however, depend on both current state and input, offering more responsiveness. While more machines offer stability, mealy machines can be more complex. Understanding these differences is crucial for effective design. Consider a traffic light controller as a state machine. It cycles through states: red, red plus amber, green, and amber. Each transition occurs based on a timer input. Outputs are the light signals themselves. This simple example illustrates the predictability of state machines. A vending machine can be modeled as a state machine. States include idle, credit, dispense, and change or reset. Inputs like coin insertion trigger state transitions. Outputs include dispensing the product or returning change. This example shows clear money-based transitions and actions. A login system with lockout is another state machine example. States are logged out, checking, logged in, and locked. Inputs like valid or invalid credentials cause transitions. Outputs include granting access or showing error messages. This system ensures security by limiting login attempts. Finite state machines, FSMs, consist of a finite set of states and transitions. They ensure predictable and repeatable behavior in systems. FSMs are widely used in control systems and communication protocols. Their finite nature makes them easy to analyze and implement. They are crucial for both hardware and software applications. State diagrams visually represent state machines. States are depicted as circles and transitions as arrows. Inputs trigger transitions, and outputs describe actions. These diagrams make system behavior easy to understand. They serve as a blueprint for implementation. State machines provide structure and control in computer systems. They ensure systems respond correctly to events. This prevents undefined behavior and maintains reliability. From device drivers to user interfaces, state machines are essential. They simplify complex system behavior into manageable states. CPU instruction processing can be modeled as a state machine. States include idle, fetch, decode, execute, write back, and halt. Inputs like start signal initiate transitions. Outputs involve control signals and fault handling. This example reflects a real control unit style FSM. A memory read-write controller uses state machines. States include idle, read address, read data, write data, and done. Inputs like read and write requests trigger transitions. Outputs involve bus signals and acknowledgements. This models how CPU requests are serviced. Printer spooling can be controlled using a state machine. States include idle, queued, sending, printing, completed, and error. Inputs like job added or paper jam trigger transitions. Outputs involve connection and alert signals. This shows how peripherals are managed. Implementing state machines involves a state variable, inputs, and transition logic. Outputs are defined for each state or transition. A clock concept ensures timely state changes. Python is great for modeling and testing FSMs. Verilog is used for digital logic implementations. A vending machine FSM can be implemented in Python. It accepts coins, vends products, and returns change. States include idle, credit, and dispense. Transitions are deterministic, ensuring predictable behavior. Testing involves simulating coin inputs and checking outputs. A washing machine FSM can be implemented in Verilog. States include idle, fill, wash, drain, spin, and done. Inputs like start and lid close trigger transitions. Outputs control valves and motor signals. This illustrates proper hardware structure and safety behavior. Testing FSMs involves running input sequences and checking outputs. Python FSMs use unit testing frameworks for validation. Verilog FSMs use simulators with test benches. This ensures state progression and output accuracy. Testing is crucial for verifying correct FSM behavior. State machines offer deterministic behavior and reliability. However, they can suffer from state explosion with complexity. Rigidity limits adaptability in dynamic systems. Inefficient design can increase processing overhead. Evaluating these factors is key to improving performance. Improvements include hierarchical and parallel state machines. Hierarchical designs reduce complexity and improve readability. Parallel machines manage independent behaviors concurrently. Optimizing transitions and outputs enhances performance. These strategies ensure scalability and efficiency. Software implementations benefit from table-driven FSMs. This reduces branching overhead and speeds transitions. Hardware designs use pipelined FSMs for efficiency. These approaches optimize performance and power consumption. Thoughtful design ensures FSMs remain effective as systems evolve. In conclusion, the ability to design and implement simple state machines is essential for understanding system behavior and control in computing. State machines provide a structured way to model processes, showing how systems respond to inputs and transition between states. Designing and implementing these models supports problem-solving, logical thinking, and system design skills. This understanding is fundamental for developing reliable systems and applications in computing and engineering contexts. Thank you for watching this video. If you have any questions, please feel free to contact us via email or WhatsApp at 07484361688.